Okay. As you can see, this was I thought I had this picture downloaded on it, but this shows refraction at its best. All right, um, because we would think that his body's here, but it's actually over here. There's all kinds of refraction taking place here. We've got the tank, we've got the light coming from his body, and then it's getting bent uh, because this is actually underneath him, and so it bends away from the normal. So it looks funny. Same thing here. We got the polar bear. These are all examples of refraction. All right. Here's another one where the person it's and it's just funny. I mean, it's pretty cool. Um, this polar bear looks, it's completely turned around. It's all messed up. But anyway, that's what's going on. So the light bends. Light bends when it goes into a different. Um, as a matter of fact, that last one that I showed was pretty good. Anyway, so I wanted to make sure that we understood refraction here real quick. So let's go ahead and click on here, and here's the deal. And I wanted to make sure that we kind of got this. So, all right. Now, we kind of talked about it briefly in chapter 20, where the speed of light is equal to lambda times the frequency, the wavelength times the frequency. Okay? All right. And then um, we know that every material has an index of refraction. Just wanted to make sure that we did this index of refraction in. And in your, on your lecture notes, they are on your slides. They give that are loaded on Blackboard for you. They give all the different indexes or refractions of different materials. Okay, and we'll work on this on Friday. And so here's lambda in the medium in a vacuum divided by the index of refraction of whatever it is, and that changes the wavelength because the frequency does not change. Okay, so we've got this. So what we have is, and what we're going to get ready to do is Snell's law. And so we've got this relationship between the index of refraction because of this. N is equal to the speed of light in a vacuum. Now look, watch closely. N is equal to the speed of light in a vacuum divided by the speed of light in the medium. Okay, which is equal to lambda in a vacuum times the frequency divided by lambda in the medium divided by the frequency. The frequencies cancel, and so you've got lambda divided by lambda m. And that's kind of where we ended yesterday. All right. And we're going to have to get used to dealing with like 560 nanometers. Okay. That can equal, that's either 5.6 times 10 to the negative 7 meters, or that's 560 times 10 to the negative 9 meters. Okay. Either one will work. But for the most part, if you're taking a ratio of the two, you can just leave it as 560 and you can get in. But when we actually have to find the frequency, or we have to find the wavelength of something, then we need to convert it to meters. All right. So this is the end of track one. Just a little intro. This is pretty much all we did yesterday. All right. And besides the fact that, one last thing, I want to show one last thing, that when the incident ray comes in and it hits the surface, if the medium has a higher index of refraction than where the ray originated from, it will bend towards the normal. If it has less, if medium 1 is greater than medium 2, then it'll bend away from the normal. Okay? And that leads us to Snell's law. Did we ever get Snell's law here? Like in a freaking equation? No, they don't. Not in the, what, hold on. I still don't see Snell's law in an equation. Do you? They've kind of got it here, but that's not good. So we can also, due to the angles that they, well, this is stupid. All right, I'm going to stop here. Please don't watch the last minute of this thing, and then we'll start here with Snell's